So in this session, we're going to continue on talking about some of the different types of dead stars, this time focusing on neutron stars. As we're going through this portion, I still recommend that you have that dead star memory matrix and fill out some of the cells with the information to kind of be able to quickly compare and contrast between the white dwarfs, neutron stars, and black holes. Again, that memory matrix is on both Lawn Kappa and Blackboard, so grab a version of that if you haven't already done that. So in this session, we're talking about these neutron stars. This is a star has gone supernova, a high mass star has exploded as a supernova and ejected its outer layers very violently. And the process that led to this neutron star, the supernova event, that led to this particular neutron star, the reaction that was powering that supernova was taking electrons and protons and fusing them together into neutrons plus neutrinos. We said it was the neutrinos that carry most of the energy of this reaction away. Again, the tiny percentage of that ridiculously large number of neutrinos, the tiny percentage of that actually hits the outer layers of the star, that's enough energy to still violently shockwave those outer layers off the star at around 10% the speed of light. But we leave these neutrons behind. So this neutron star is really just this giant ball of neutrons. And we currently don't know too many of the details of how matter exists in this crazy, crazy extreme state. So essentially, this is a giant ball of neutrons. What supports this against collapse is something called neutron degeneracy pressure. We've talked a bunch of times about electron degeneracy pressure, where electrons don't want to be in the same quantum state. Well, neutrons, if you get them close enough together, neutrons will do a similar kind of thing. So they don't want to be in the same quantum state, and that force is literally the only thing supporting this thing against collapse. So they're supported by neutron degeneracy pressure. Which again is very similar to that electron degeneracy pressure. We talked briefly before about this Crab Nebula. This is the remnant of a star that exploded in the year 1054. At least that's when astronomers on the Earth observed this. Since it's far away, it would have had to have exploded earlier, and that's when the light from this exploding star reached us. And this is in the visible part of the spectrum. If we look at the X-ray part of the spectrum, there's actually a very strong X-ray source right at the center of this thing, and that is one of these neutron stars. General properties of these things. These neutron star masses are between 1.4 to 3 solar masses. So even the lowest mass of these neutron stars is more massive than our sun. Our sun will never end up as a neutron star. It's going to end up as a white dwarf, since our sun is considered a lower mass star. Yet despite this huge mass, they're only around the size of a city. So about the size of a city. Which again makes these some of the weirdest and most extreme physics areas, regions that we see in the universe. Remember when we were talking about atoms, and we said if an atom were the size of a classroom, the nucleus of that atom, where the protons and neutrons are, and where 99.8% of the mass would be like a speck of dust in the middle of that classroom. Well, these neutron stars, all of that empty space has been eliminated. Remember, in the supernova explosion that produced this neutron star, all of the electrons fused with the protons in order to just make more neutrons. So all that big empty space that we said, oh, this is where the electrons kind of swarm around the atom, that space is gone. So these are incredibly dense objects. 1 teaspoon of this neutron star material would have the same mass as a mountain. These are exceedingly, this is about as dense as matter can get. So density, 1 teaspoon is around Mount Everest's mass. And again, we still don't have a very good understanding of just what matter is like under these ridiculously extreme conditions, because we can't produce these kinds of extreme conditions on the Earth. Again, this neutron star material is material under some of the most extreme conditions in the universe. So again, since we have a lot of mass in a really small area, and we can get close to this object, the surface gravity of this thing is so high, in order to escape it, you'd actually have to be going at around 70% the speed of light in order to escape this neutron star. Okay. Again, since all this mass has been compressed down so small and we can get really close to that mass, it's going to have an extremely large gravitational field. There is a subtype of neutron star called a pulsar. It's a subcategory of neutron star. So all pulsars are neutron stars, but not necessarily all neutron stars are pulsars. These neutron stars have very, very strong magnetic fields. So very strong magnetic fields. And presumably the reason for this, again, there's still a lot of open questions about these neutron stars and these pulsars, but presumably the reason for this is when we have a star like our sun, it has magnetic fields. When you take that star and have it collapse under gravity, like the core does during the supernova event, the core collapses, the outer layers get blown off. When that core collapses, all of those magnetic fields, all those magnetic field lines collapse along with it and kind of magnify. Those magnetic fields get far, far stronger. And these objects are also going to be spinning very rapidly. I've already done this demo a couple of times with me holding some masses and spinning around, and when I pull my arms in, I start spinning far faster. Well, again, here we have a star core that has collapsed down to about the size of a city. So these objects are spinning very rapidly. So rapid spin. And the combination of this strong magnetic field that is rapidly spinning will actually produce a beam of radio waves that will extend out of the north and south pole of that neutron star. So it produces a strong beam of radio waves. This leads to some really interesting consequences because the magnetic axis of this neutron star, the direction that that radiation beam is being fired off in, is generally not going to be the exact same as the rotation axis. So as this thing spins around, that beam of radiation is going to be pointing in all sorts of different directions. And if we are at the Earth's location and the Earth happens to be in the right position, as this thing spins around, every rotation, that beam of radio waves is going to be pointed towards the Earth. So this kind of acts like a lighthouse in space. As this pulsar spins around, once every spin, it fires that beam of radio waves at us. And if we are observing this with a radio telescope, we will get this little burst of radio waves. We will get this little pulse, hence the term pulsar. And the rotation of these pulses the rotation rate of these pulsars matches the pulse rate that we detect. So we can actually detect how fast are these pulsars spinning. So we get this lighthouse in space effect. Where every time the pulsar spins, it aims this beam of radio waves at us, and we get this little blip on a radio telescope. And these pulses, we find them to be exceedingly regular. This spin rate is very, very regular. In fact, the first time these pulsars were discovered, the first discovery of these pulsars by an astronomer by the name of Jocelyn Bell. She was, I think, a grad student at the time and doing some radio astronomy, and noticed these sources that started going blip, 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 blip with extremely high regularity. Astronomers for a while were trying to figure out what are these things. In fact, the first pulsar was given the moniker LGM for Little Green Men, because one of the potential hypotheses was that this is some sort of navigation buoy for some extraterrestrial intelligence. Of course, saying it's aliens is probably going to be our hypothesis of last result, because there isn't much of a way to test that. So as scientists were starting to think of, well, what else could this be? This idea of a neutron star had already been thought of. The idea that they could have very strong magnetic fields and could be spinning very rapidly kind of led to, oh, well, maybe this is one of those neutron stars, a kind of neutron star. So again, when we detect these pulses using radio telescopes, I'm hoping that the sound is going to show up okay come through okay on here. If you have headphones on, you might want to take those off in case I don't have the volume level right. But this is the radio signal from one of these pulsars sent through a speaker. Again, what we are receiving is a form of light, radio light, but we're changing it into a sound file to kind of represent that. So this is what it sounds like. So every one of those clicks that you're hearing, that's this pulsar aiming its radio waves at the Earth during each one of those spins. Now, again, it was not really seriously thought that this might be aliens. It was like, okay, there's probably some reasonable explanation for this. But when people were coming up with the idea of, hey, maybe this is a spinning neutron star that's emitting these powerful radio waves, well, are there any spots where we think there might be a neutron star and might be able to detect this? Well, what about that Crab Nebula? The leftover remains of that star that we saw explode in the year 1054. Maybe there's a pulsar there. So we aimed radio telescopes at it, and this is the resulting sound. Again, be careful if you're using headphones for this one. This was the resulting signal that we got. That one's spinning a little bit faster. Again, each one of those clicks that you're hearing, that really rapid pulse rate, that is this thing spinning around 30 times every second. This is one of the really extreme cases of we have this spinning object, and as it collapses, that spin rate is going to increase. But this Crab pulsar isn't even particularly fast for neutron stars. There's a special class of pulsars that have actually accreted more material from a nearby neighbor, and as they pull in more of that spinning material, It's like, again, the figure skater pulling their arms in, spinning faster and faster. And some of these pulsars can spin hundreds of times per second. We call these millisecond pulsars because their rotation times are measured in milliseconds. So this is JO437, and this is what its pulsar signal sounds like. This thing is spinning so fast that you can't actually hear the individual pulses. It sounds like a tone. Again, this neutron star is something more massive than the sun, the size of the island of Manhattan, spinning faster than a blender. And these millisecond pulsars, one of their interesting properties is that they can tick with a long time scale reliability that rivals the accuracy of atomic clocks. There are actually researchers who are developing methods to use these pulsars, the special class of millisecond pulsars, as a more accurate way to measure longer times. Again, atomic clocks can tend to drift over longer times. These millisecond pulsars seem to have a higher level of reliability for longer time periods. So for this part, I just want to talk about some of the crazy properties of these neutron stars, because like I said, they are some of the most extreme objects that we see in the universe. So my objective with this slide is to just get people to say, holy crap. Let's see how I do. So if you dropped an object from 1 meter above a neutron star, its gravitational field is so strong that it would hit the ground a millionth of a second later, traveling at 2,000 kilometers per second. Don't drop it on your toe. What about this? Suppose we had a ball of neutron star material here. Well, what it would do is it would violently explode because the ball of neutrons doesn't like to be in that configuration. In a neutron star, it's held together by gravity. So if I had a ball of neutron star material here, it would explode with the force of probably a few thousand nuclear bombs. But let's say we could magically keep it in that neutron star density. If you drop that, the fact that there's ground there wouldn't really matter. It would just start cutting its way through the Earth repeatedly until friction eventually caused it to settle in the Earth's core. If there was a teaspoon of this neutron star material just at the side of the room over here, I would be hard pressed. I would have to be holding on to other stuff in order to not just slide that way. What else? Well, the gravity around a neutron star is so strong that it'll actually bend the path that light takes. If there was a neutron star over here, some of the light from the backside of that neutron star will be affected by its gravity in such a way that when light is emitted by that backside, the gravity actually bends the path of that light around the neutron star. So if you are at some location and looking at this neutron star, you'd be actually able to see part of the back of this neutron star because of how it bends light around it. You'd actually be able to see around 70% of the surface of that neutron star, not just the ordinary 50% that, usually if you're looking at just a sphere, you can see half of the sphere at any one time. This neutron star, based on how it bends light around it, you could see around 70% of it. Well, still not there. Let's try this one. I said that the magnetic fields of these neutron stars were very powerful. Well, how powerful is powerful? If one of these neutron stars was at the location of the moon, the magnetic fields would be strong enough to wipe every credit card and every hard drive on Earth. If one of those were in New York and we're here in Ohio, if a neutron star was in New York, the magnetic fields alone would be able to take the water molecules in your body, and water molecules are polar. One side is positively charged, the other side is negatively charged. And those different charges move differently in strong magnetic fields. this magnetic field would be so strong that the two sides of that water molecule would literally be ripped apart as they move around. The water molecules in your body would all simultaneously explode. Of course, that may not be the thing that kills you, because if one of these neutron stars were actually in New York, the entire Earth would fall onto the neutron star and become this, a couple centimeter thick new crust for this neutron star in, a few dozen seconds, probably. So let me know if I achieved my objective with this one. So these neutron stars, if they're left on their own, kind of like the white dwarf, they don't do all that much. The neutron stars and the pulsars gradually radiate away their angular momentum, lose their magnetic fields, until they just kind of fade away and no longer can be detected. However, if we have one of these neutron stars in a binary system, well, just like the white dwarfs, if that neighbor star starts puffing up into a red giant, starts expanding its outer layers into a red giant, if some of the outer layers of that star get too close to this neutron star, it's going to start pulling in some of that material into an accretion disk. And again, these accretion disks, as material is pulled in, those different layers of material are going to rub against each other. And just like rubbing your hands together, it's going to generate an immense amount of heat, to the point where the temperatures of the gases in these accretion disks can literally reach millions of Kelvin and can strongly give off X-rays. So we've detected cases of a neutron star in orbit around a main sequence star, and the strong X-rays that are actually being given off by this accretion disk, those high energy sources of light actually cause the outer layers of this star to puff up in their own right. So there's actually some interaction between these two stars. They're not going to be just acting and evolving in complete isolation from each other. When material is pulled onto these neutron stars, again, it's hitting the surface of the neutron star going at around 70% the speed of light, going really, really fast. And again, in a similar fashion to the white dwarf novas that we talked about, when some of that captured hydrogen falls onto the surface, we can get a strong burst of hydrogen fusion on the surface, and we get these X-ray bursts. So this eruption of hydrogen fusion on the surface can release 1,000 times more power than the sun in just a few seconds, all in X-rays. Remember, we said 1 second of the sun's power output would satisfy current worldwide energy needs for the next 500,000 years. The power output of one of these X-ray bursters can be around 100,000 times larger than that, at least for a few seconds, and all of that energy is going to be in the X-rays. So again, these neutron stars are extreme objects. This is the most extreme densities and pressures, and we still don't have a very good understanding of exactly how matter works in these extreme cases, but neutron stars give us an opportunity to study some of these properties. So we'll finish off talking about the last type of dead stars, black holes, in the next session.